Testing. 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 Can I get it? Testing. Okay. We are live. Let me make sure this is off. Alrighty. So, welcome back to another Hoopo stream. It's been a second since we've actually done one of these, so let's get back into the groove. Today we're going to be looking at two different repos. So, I found these two repos that both claim to be a fast version of the SAM, S-A-M, otherwise known as the Segment Anything model, which is a foundational model for segmentation coming out of Meta. So we actually read that paper a while ago now. It's a little bit older, but that's why we're starting to see variants of it. Reposition this. Okay. So both of these are different ways of making it faster, and I'm curious how they made it faster and what type of little tricks they've added to it, right? So we have a couple different things pulled up here. We have, both of these have GitHub repos that both seem to work. Both of them have Hugging Face demos, and both of them have, of course, papers. So maybe the first thing we should do is just kind of read the abstract and kind of get an idea of who are these different groups that are publishing these faster Segment Anything models. So we got the first one here called Fast Segment Anything. It's coming out of Wuhan AI Research. Object Eye Inc. I don't know what Object Eye Inc. is. Probably a startup. Let's check. Object Eye Inc. Object Eye valuation. Okay, so it's basically 7-10 mil, maybe like a Series A, early stage seed round in 2018. Okay, so this is actually a pre-generative AI startup, but you can bet they're probably using some next level things at this point. You have University of Chinese Academies and Sciences, Institute of Automation. Okay, so a couple different Beijing universities there. Let's compare that to this other paper. So this other paper, Kyunghee University. This does not sound Chinese. That sounds Korean. Let me check. Kyunghee University. Kyunghee University in Seoul. Okay, so yeah. So basically you got one paper out of China and then one paper out of Korea. Both of these papers coming out very, very similar here. We got 21 June 2023, and then for the other one here we got 1st July of 2023. Okay. This one called itself Faster Segment Anything. All right. Recently proposed Segment Anything model has made significant influence in many computer vision tasks. I would say specifically segmentation. I don't think this is doing much for other things. It is becoming a foundation step for many high-level tasks like segmentation, image captioning, and image editing. However, its huge computational cost prevents it from wider applications in industry scenarios. So, yeah, if I recall, I think the vanilla Segment Anything model that we were looking at was basically this huge encoder, and then it also had what they called a mask encoder or something like that. Basically, like, you can prompt it in different ways and it turns that prompt into let me see. Let's look at the original Segment Anything. Yeah, right here. I want the actual paper, not whatever the fuck this is. Right here. So I think this is the original one, yeah. Let's go back up. I'm getting distracted. All right, let's go to this one. Segment Anything. This doesn't actually look like the original paper, but I think it is. But yeah, so you have your image, and the image is getting fed into the image encoder, which is just a giant vision transformer. And then these are the two other main components here. You have the prompt encoder. That's what I accidentally called the mask encoder. But basically the prompt, there's different types of prompts that you can give it, right? You can give it points, so you can define a bunch of XY points in pixel space, and then those are used as kind of the segment what this object is. You can give it bounding boxes, and you can also give it segmentation masks, and then the text is actually the coolest part. So you can prompt with text. But any one of these types of prompts are fed into this prompt encoder, and it gets turned into some vector that represents that prompt, right? So no matter what your original input is or what your original prompt here is, it'll get turned into some vector that represents what that prompt is. And then there's an additional model, which they call the decoder, which then consumes that prompt representation along with the image representation, right, after it's been fed through this giant vision transformer, and it'll actually give you the mask for that. So I think most of the compute is probably this image encoder, to be honest. That's probably the biggest model. I don't think the other two are as big, but also the fact that you have to feed it in kind of sequence like that. Yeah, here's a better, this is the image I remember. Even the fact that you have to basically feed these things kind of in sequence, I think, is part of the problem as well, right? Is that the mask decoder needs the input or the output of the image encoder and the output of this prompt encoder to do its job. So you have to wait to perform inference on this mask decoder until you perform inference on the image encoder and the prompt encoder. Okay. So that's something that they could potentially do, is be more tricky about that. The computation mainly comes from the transformer architecture at high resolution inputs. Yeah, so this is basically the vision transformer that's taking your raw image and converting it into this image representation that's going into the mask decoder, right? And of course, there's some power law there. There's probably, the bigger you make that vision transformer, the better the performance. So you have a little bit of a trade-off. In this paper, we propose a speed-up alternative method for this fundamental task with comparable performance. By reformulating the task as segments generation and prompting. What the fuck is this? Segments generation and prompting? Prompt here is getting overloaded. This term means a lot of different things. I think nowadays when most people talk about prompting, they're talking about text that is being used to prompt like a language model. But here, the prompt is kind of you as a user, what part of this image do you want to segment? Right, so whenever they say text, you could say a scissor. You could say like a sequence of text that represents the fact that I want to segment this scissor. Points means that you're clicking on the image, so it's basically XY tuples in image space, and then boxes, and also XY tuple, but also with width and height. So the prompt in the context of segment anything models means different thing. Find that a regular CNN detector with an instant segmentation branch can also accomplish this task well. Oh no. So maybe they get rid of the... okay, I see what they're going to be doing here. All right, I kind of like sneaked here at this image, and now I'm getting an idea. All right, let's finish this abstract, then we'll go into it. Specifically, we convert this task into the well-studied instance segmentation task and directly train the existing instance segmentation method using only 1/50th of the SA1B dataset published by the SAM models. This is the Segment Anything 1 billion dataset. And the interesting thing about the Segment Anything paper is that the way that they train this, they actually did this kind of like self-supervised, kind of like pseudo-labeling, where they would originally provide some labels, right, and then train on those, and then that model at that checkpoint would be used to label a bunch of new images, and then those labels would be used again to train the model. So over the course of the training, the size of the data set increased, and the model increasingly labeled the data that it would be trained on, right? And then I think they also had like so they call this the semi-automatic stage. But they also had humans in the loop. So they would have humans that would basically go and look at the masks. Yeah, are professional here. Annotators to improve the quality of the masks and so on. So it's kind of like this weird loop. I would call it self-supervised, but I don't think they use that term. They used semi-automatic and automatic. So I think what they're describing here, the SA1B dataset is at the very end of all of that. So that's the full dataset with everything labeled. With this method, we achieve a comparable performance with the SAM method at a 50 times higher run speed. So that's really fast. You know, even just 2x is fast, but like order of 10 is super impressive. We give sufficient experimental results to demonstrate its effectiveness. So here we have the actual picture. So we have a car. It's being given to fast SAM and to SAM. That's kind of a weird way to say that one of these is faster. You wouldn't be feeding the same image to both of them unless you wanted to compare or something. Looks like fast SAM is 40 milliseconds per image, and then the original SAM is 2,000 milliseconds per image. And here, looking at this figure, you basically get an idea of what they did, right? So in the original segment anything model, the encoder is a vision transformer. So this thing here, this image encoder, is a giant vision transformer, right? But if you actually look at here, you see how they have VITH. This is the huge vision transformer. 16 by 16 refers to the number of patches. So vision transformers, they break up the image into this sequence of patches, and then they feed each of those patches into this transformer-based architecture that kind of almost reads it like if it was a sentence, right? A sequence. But you see here in this paper, fast SAM, you see YOLO V8X. So YOLO V8 is a kind of an older style ConvNet model. It's used for mainly object detection, but I think what they mean here is they're using the encoder in the YOLO V8 model, right? So even let's actually see what the YOLO V8 model looks like nowadays. Ultralytics. So this is I do recommend this. Ultralytics is like I want to say framework or something like that, but basically it allows you to use YOLO with nice little clean Python bindings. Do we have some kind of like model cards? Yeah, here we go. Okay, so YOLO v3 is the OG one. YOLO v4. Darknet is actually pretty crazy. If you guys don't know about this, Darknet is basically like an implementation of like, it's like TensorFlow or PyTorch, but written from scratch by this guy, Joseph Redman. I doubt that they actually continued to use it. I'm sure they ported it and eventually in one of these V7 or V8 or V6 turned it into Python, but at one point it was written in its own framework. YOLO v5, v6, v7, v8. Okay. So YOLO v8, what is the backbone for this? State-of-the-art backbone. So whenever they say backbone, that's the same as this encoder here, right? Sometimes they call them encoders, sometimes they call them backbones, but basically what it is, it's a neural net that takes this image and converts it into a vector, which they call an embedding here, but this vector represents that image, right? And it's a much lower dimensional version of that image than the actual full image. So do they actually tell us what the backbone is here? So obviously you have different heads for this, right? So the backbone for all these different tasks is probably going to be the same, right? So you have segmentation, classification, pose detection. These are different detection problems. Segmentation is labeling, almost like classification per pixel, which is the same thing that these models are doing. Classification is just your standard like ImageNet, like is this a dog, is this a cat? And then pose is whenever you see like the skeleton of a human or like the skeleton of like a hand or something like that, you're trying to track individual joints and their relationship to each other. But what I'm looking for here is the actual backbone architecture, but they don't even tell us. Okay, maybe they tell us here in the paper. But we know that it's a ConvNet, so TLDR, they're replacing the giant vision transformer in the segment anything model with the very fast, efficient ConvNet backbone used in the YOLO model. I don't know what this TRT stands for. Uses tensor RT. Okay, so Both SAM and FastSAM are tested using PyTorch, except FastSAM TRT uses TensorRT. So, okay, so TensorRT basically seems like some PyTorch alternative that's faster at inference. I feel like I've heard of this before, TensorRT. Enables you to optimize inference using techniques such as quantization, layer, and tensor fusion, kernel tuning, and other NVIDIA GPUs. Okay, so it's basically like CUDA's own little inference optimization framework. So, I mean, they say quantization here, so it allows you to use quantization, but they don't mention quantization here, and I feel like that would probably be a way to make it much faster, right? Quantization is the process of using smaller data types, so you don't have to store the entire model in a very large data type. So basically, each individual parameter in the model takes up less space and is faster to compute with. That seems kind of on par with the speed up there. You go 40 milliseconds to 12 milliseconds, so that's like a 4x speed up. Okay, and then what do we got here? So this is frames per second, recall at 50% precision. So recall is a way to measure the performance of a detection model or any kind of you have precision and you have recall. Recall is basically how many can you actually find. I love to show this recall versus precision. There's a very good picture on the Wikipedia here, true positives, false positives. So you see how recall is basically how many true positives you get out of how many total positives there are, versus precision is how accurate you are, if you want to think of it that way. It's out of all of the ones that you get, how many of them are the actual true positives. True positives is whenever you're supposed to detect a cat and you do detect a cat. False positives is whenever you maybe say that this dog is a cat, and then false negatives is there is a cat in the image but you can't detect it. So here they're basically saying that the original segment anything model is better, has a higher recall, right? The higher the recall is, the better, but it's significantly slower, right? So kind of the idea I'm getting from this abstract and this first figure here is that largely what this fast segment anything paper is they're replacing the image encoder with a much faster ConvNet, this YOLO V8, and you're getting a little bit less performance, but you're getting significantly faster but less performant. Yeah, I don't know if this is necessarily good because the secret is that YOLO V8 is faster now, but I think over the next couple years, the hardware is going to get better and better at making transformers faster, right? So, and nobody's really trying to make hardware that makes ConvNets faster at this point, right? Because ConvNets are already a decreasing niche within the deep learning world. So I think that you're going to see hardware that is more and more optimized to improve the speed of transformers. So I feel like using ConvNets right now seems like a good idea because it'll be faster, but I think 5 years from now, the vision transformer, even if it's bigger, will be faster than this ConvNet just because of the incentives in the hardware race. Okay, so that's kind of, I think, what's going on with this one. Zork24, TensorRT can definitely do quantization. Yeah, so we did see that, how here it does allow for quantization. They just don't explicitly mention it, right? I feel like if they did do quantization, they would have said it, right? They would have said like FastSAM quantized and then FastSAM, but maybe they haven't even done it. And then there could be another square over here that's even faster. Okay, let's go to this other paper. So that was the first paper, was the paper coming out of China. This is the paper coming out of Korea. ConvNets will probably stay faster. I don't know. I think that the amount of money going into making transformers as fast as possible, especially inference for LLM use cases, means that to me at some point there's going to be a turning point where if you're doing convnets, it's going to be slower, even for something that is smaller and should be way faster. But I mean, that's also just me trying to predict the future there, right? I have no idea. Okay. So here you see a preprint. Whenever you see a preprint, that basically means it's not actually published yet. They're just putting it out there. But the machine learning world moves so quickly that at this point, you pretty much only read the preprints, and then by the time they actually get published and released officially, like, you're already on to the next thing. Okay, we got segment anything model has attracted significant attention due to its impressive zero-shot transfer performance and a high versatility for numerous vision applications. Impressive zero-shot transfer. So I guess here kind of what they're talking about is that outside of the distribution it was trained on, right? So the model was trained on this 1B data set. Where is it? Right here. Actually, we have it over here. The model's trained on this 1B data set, which I feel like it's going to be pretty huge. But if you try to then use this model on an image that is not part of that data set, an image that is out of distribution, say, for example, like an X-ray image, right, you would expect the performance to be not as good. So one of the magic pieces of the segment anything model is that because the data set it's been trained on is so big, and because the system itself is relatively generalizable. I don't know what the right word there is, but because the vision transformer encoder is pretty good at encoding pretty much any image, it's able to get zero-shot transfer performance in weird domains like X-rays or depth images or something like that. I would say the high versatility is honestly the coolest part of the segment anything model, right? The fact that you can prompt it with text, that was the most impressive part to me, right? The fact that you could say, here is, or I want the scissors, and it takes that text, converts it into this prompt. This prompt gets fed into this mask decoder, which also consumes the image, and it'll actually give you the scissors. I think that was some next level things, some next level versatility, utility. I don't know. My brain isn't working yet. Many such applications need to be run on resource-constraint edge devices. So edge devices means on the edge. So anytime you see this edge, it means basically close to the customer, right? And who is the customer? So the customer could be you on a cell phone. So if you're sitting there on a cell phone and someone says, I'm running something on the edge, they're running it on the very edge, which in the case of you on a cell phone means the cell phone. They're running it on the cell phone. If someone is in a robotics world and they say, hey, I'm running things on the edge, then what they mean is they're running it on the robot. So edge doesn't mean a specific type of computer. It just basically refers to at the very edge of the application, which usually ends up being a smaller thing, like a cell phone or like a Raspberry Pi or some kind of little NVIDIA Jetson on a robot. But the key thing about edge devices is that they have constrained resources, right? They're always small. They're always tiny. It's always a pain. You always have to quantize everything as much as possible, and then even then it barely works or it barely fits. So very hard to fit a giant pre-trained vision transformer into a edge device. In this case, mobile phones. But this would also apply to robotics things like the NVIDIA Jetson. We aim to make SAM mobile-friendly by replacing the heavyweight image encoder with a lightweight one. Okay, all right, so it kind of seems like this paper is doing the same thing as the other one. All they're doing is they're basically replacing this giant image encoder. So that's a little sad. It seems like both of these papers came to the same conclusion. I thought there might be like something more tricky, more interesting, but I don't know. Let's see if they do it actually differently. A naive way to train, such as new SAM is in the original SAM, leads to unsatisfactory performance, especially when limited training resources are available. We found that this is mainly caused by the coupled optimization of the image encoder and the mask decoder. So anytime you have an encoder and a decoder like this, right, these have to be kind of trained in tandem, because one way to think about what the encoder and the decoder are doing here is that the encoder and the decoder are learning a language together, right? They're communicating to each other via a little vector that represents a meaning, right? So in the case of this segmentation pipeline, what the prompt encoder is doing is it's taking a set of points or a bounding box or a text description of what you want, and it's turning it into this little vector that it can communicate to the decoder with. And the decoder can take that little vector and say, oh, okay, this is what you want in the image. All right, here, I'll give you the actual mask for that, right? But if you take this encoder and separate it from the decoder, or vice versa, and then start pushing gradients into the encoder and start pushing gradients into the decoder, they're going to start to drift, and that language that they used to communicate in is going to become less and less consistent between them, right? It's like they're no longer communicating the same language because you've kind of pushed gradients separate to each of them separately. So this decoder and this encoder are kind of a little pair, right? They're little buddies, and you don't want to separate them for too long, because if they start to drift apart from each other, then they're not going to perform as well together. So that's my anthropomorphization of the day right there. Motivated by which we propose decoupled distillation. Okay, so maybe some fancy way of uncoupling the encoder and the decoder, and distillation generally refers to, there's a lot of different types of distillation. You have dataset distillation, which is reducing your dataset down to a small representative dataset. Sometimes you call, distillation is the process of taking a teacher network and using it to basically train a smaller student network, and that's distilling, right? And distilling is just the process of taking something that has more volume and reducing it into small volume, right? It actually, that's how people make alcohol, is they distill basically something that's the concentration of beer, and then they distill it into something that's the concentration of like a spirit. So that's where that word comes from. Concretely, we distill the knowledge from the heavy image encoder to a lightweight image encoder. Okay, so I think that's basically what these guys were doing as well. Did these guys talk about the exact approach? So these guys, the way these guys mentioned the original SA1B dataset, so this almost makes me think that they trained the new image encoder from scratch with the original dataset, versus in this paper they're distilling the new encoder from the original image encoder. So in this case, right, when they say distill the knowledge from the heavy image encoder, what they would be doing is they would be taking their new lightweight image encoder and the heavy image encoder, they feed both of them the same image, and then they have a loss that says, okay, well, the lightweight image encoder should produce the same output vector as the heavy image encoder, which can be automatically compatible with the mask decoder in the original SAM. The training can be completed on a single GPU within less than 1 day, and the resulting lightweight SAM is termed mobile SAM. Okay, so these guys love the mobile phone. Kind of seems like the driving design decision here, which is more than 60 times smaller, yet performs on par with the original SAM. For inference speed on a single GPU, the mobile SAM runs around 10 milliseconds per image, 8 milliseconds on the image encoder, and 4 milliseconds on the mask decoder. So this kind of gives you an idea of like just how much of the inference is actually dominated by the image encoding. With superior performance, our mobile SAM is around 5 times faster than the concurrent fast SAM and 7 times smaller, making it more suitable for mobile applications. Moreover, we show that mobile SAM can relatively run smoothly on CPU. So why is this important? A lot of times on your edge, right, on your edge devices, you might not even necessarily have something that looks like a GPU, right? For example, like a Raspberry Pi. Raspberry Pi doesn't have a GPU on it. You have to run it on the CPU, right? Although I think at this point, I feel like most modern cell phones are going to start to incorporate GPU-like computational chips, and then obviously like your like NVIDIA Jetsons are going to have a huge, not huge GPU, but comparatively huge GPU. I think they even make Raspberry Pis, like the Google Coral. Yeah, this is like a Raspberry Pi, but it has a little GPU on it. So I don't know. Maybe CPU inference is less and less important over time. The code for our project is provided with a demo showing mobile SAM can run relatively smooth on CPU. Okay, so here we have basically very similar to the original figure in the segment anything. They even use the same colors, so props to that, you know. I love consistency. So you have your images, you have your image encoder. This is the vision transformer based encoder. They're calling it the heavyweight. That's creating image embeddings. Oh, wait up. This is a little bit confusing here. They're saying they're turning the heavy image encoder into a lightweight image encoder, but here they use the word lightweight to describe the prompt encoder. So this is a little weird, because I think what they did is I think this might be wrong. This is giving us the wrong intuition. Yeah, I think the prompt encoder is the same. I think the prompt encoder and the mask decoder are actually the same, so they didn't fuck with these. These are the same as the original ones, but this is the one that they changed from a big model to a small model. But, okay, so both of these papers are effectively doing the same thing, but with slightly different Let's see if we can scroll and we can find the exact backbone that they use here. From semi, decoupled, VIT-based, small image encoder. That is still the overview of the original SAM, yeah. So I think maybe what they were just showing you is that in the original SAM, the prompt encoder and the mask decoder are actually quite small. Really, it's just everything comes down to that image encoder. Okay, so we know that in this paper they're using the YOLO model, right? The YOLO image encoder. But here, what I'm trying to find is which one are they using here. So lightweight image encoder. The goal is to obtain by replacing the default VITH with a lightweight image encoder, a VIT-based backbone, VIT tiny, has similar parameters but performs better. Okay, so this is, here's a little typo actually, this should be tiny, not yiny, but, okay, so here we have actually a difference between these two papers. This one is replacing the VITH, the huge vision transformer, with a VITT, which is a tiny vision transformer. So still a vision transformer, just a small one. And this is where they're going to use the distillation to basically make this small vision transformer try to behave as similar as possible to the huge vision transformer. But honestly, that's kind of weird. I don't know why they would necessarily care, because I feel like the original segment anything model came with a small vision transformer as well, right? Wasn't there a small vision transformer that you could use? Okay, so maybe not. So by default, the segment anything uses this VITH, and I think they also provide a VITL and then a VITB. But this VITB, if we actually look here, it's 358 megabytes. Right? So let's actually show in folder. Properties. Yeah, so even the smallest one that they provide with the original segment anything paper is actually quite large, so they're going even smaller than that. Yeah, so you go from 632 million parameters to 5.78 million parameters, which is way smaller. Looks like they're also doing... Actually, they are using convolutions here. Convolution blocks. 4 stages. At the beginning of the model, there are 2 convolution blocks with a stride of 2 for downsampling of resolutions. So the stride is basically you take that little convnet kernel and you're basically moving it across the image. And if your stride is 1, you're going across pixel by pixel. If your stride is 2, you're basically skipping pixels, so you're downsampling your output, right? And every time you downsample, you reduce the total amount of the size of the image, right? And then that basically means that any step after that will be faster. because there's just less things to compute. Note that other efficient image encoders can be adopted as the image encoder. So, I mean, that's basically what they're doing in this paper, is they're using the YOLO one. Okay. Ooh. So let's see if we can look at a little demo here. So both of these have Hugging Face demos. Hugging Face, if you guys, I feel like you guys definitely know what Hugging Face is if you're watching this kind of video, but why don't we use the same image for both of these? So let's actually copy save image as. Let's call it car.jpg, save. And then we'll also use it for this demo. Just so we use the same image for both of these. Come on, car.jpg, select. Add mask, remove area, start segmenting, click. All right, so how long did that take? Let's try it again. 0.8 seconds, about 2 seconds, something like that. And let's see what it took here. So this is the input size. Yeah, so you can actually maybe change the size of the image and do it faster. Try it again. This one takes a little bit longer, but I think it's just because the size of the image is different. Let's try the smallest size. Yeah. Okay, so I mean, they're both pretty fast, pretty quick. So you see here, I'm putting these points. So the way that the original Segment Anything paper implemented this, you could feed this prompt encoder with a set of points, and whenever you see this, right, with all the stuff already labeled, basically the way that this is actually implemented is they take a grid of points and then they put this grid of points all over the image. So whenever you don't see any kind of prompt in their vocabulary, really it means that it's just a grid of point prompts. So here you would basically, it's like if you were going like this and you were basically doing this. You see, and just putting points in a grid. So if you hit the segmentation there, you see how like basically those points are trying to tell the model that there's an object here, right? And those points are what's going into here, into this prompt encoder, and then that's converting it into that secret language that it can talk to the mask decoder with. I think the original SAM has support for 3 sizes of encoders. Yeah, so you're talking about the image encoders. Yeah, there's 3 different sizes of the image encoders used in the original SAM model. You know what's actually interesting is that they probably, these 2 VITL and VITB, the smaller encoders that they provide here with the original Segment Anything, are probably also trained with knowledge distillation, right? I bet you they spent all of their compute to just train this VITH, and then they basically just knowledge distillationed the VITL and the VITB from the VITH. So they effectively did what they did in this paper. Okay, but I mean, the demo that both of these teams provide is basically identical, right? This is like exactly the same demo. Can I look at the files? See what they're actually doing here. Mobile SAM. CUDA VIT Tiny. SAM model registry. You got your automatic mask generator. You got your SAM predictor. I kind of vaguely remember some of these. I feel like we were messing around with Segment Anything model. Here they're actually resizing, so you see how they're resizing here to the input size, scaling it. So you know they're hardcore. The comments are in Chinese. Okay, what about this one? FastSam. Let's look at the files. app.grad.io. I like that. I like the emojis. Also, it's actually very, very similar code here. This is identical code. See that? Look at that. So both of them are copying from the same exact place. Fast process. Get the points. Okay. Now let's look at the GitHub repos. Okay, so we looked a little bit at the papers. We looked a little bit at the Hugging Face demos. Now let's actually look at these two GitHub repos and kind of compare them a little bit. So we're going to move this here just so we can very quickly toggle between them. So Fast has about 4K stars. This one here has about 2K stars. So we can actually open up a new here. Let's go GitHub stars. Star history. This is a great website. It lets you see how the stars got added over time. So let's go ahead and copy the name of this here. Put that one there. And we can copy this one here. Okay, so this is a organic looking growth curve to me. Sometimes when you look at these star curves, you'll see like these like almost like a bump, right? Like this like vertical jump. And sometimes that's indicative of people buying stars. So you can actually buy GitHub stars. There's a lot of people that do that. It's a little bit nefarious. I think that if you do that, you're cheating and you're a bad person, but you know, it's competitive and people care. So, but these look like kind of organic growth charts to me. Very, very close. It looks like the Fast SAM is a little bit more popular than the Mobile SAM, but they're about on par. Okay. Let's look at the insights. Let's open insights there. Let's look at the commits, or actually no, contributors. And let's do the same thing for this paper here. Contributors. Okay, so what I'm looking for. So I'm seeing this person here, ZX Deep Diver and Yinglong Du are really the main contributors here, and you see how they pretty much committed everything at the beginning and then they kind of stopped. So it doesn't seem like they're making any changes, which is pretty standard for a kind of like a research paper, right? You kind of push all your code and then you go and you take a vacation. So it's not like a framework where you're constantly kind of updating. Similar kind of story here, right? Just a huge amount of commits at the beginning and then everything else is dead. This is just people who made little bug fixes here. This is a smaller team here. You see, you basically have one person did everything. You have maybe two people on the next level, and then the rest is just bots. Here you have a little bit more. You have one person that did a bunch of things, then you have maybe 4 other people who contributed, and then this is the bots. I call them bots, but I mean they're actually probably real people. Okay. So in terms of contributing and contributors, kind of similar stories for both of them. They look very much like a paper project. What is this? Detect branch, CNN backbone, FPN. This is old school. So in the original Mask RCNN, there was this here. Mask RCNN. Let's bring up the OG. This is an original detection and segmentation model, and the way that this model worked, so this is quite old at this point, but basically you had you had a backbone that converts the image into latent space or an image embedding. Then you had basically a network that proposes bounding boxes, and then within those bounding boxes, the segmentation is only done at the bounding box level, right? So there's a network that receives basically just what's inside this bounding box, and that's the network that actually calculates the mask, right? So you have a bunch of different networks inside these original segmentation models. That's not the way that segment anything works, right? Segment anything doesn't have this concept of like regions and then region proposals and then feeding each of those regions into a separate network, right? All of that is kind of put into this prompt encoder, mask decoder, right? All of that is removed. You don't have to do any of that crap anymore. And basically this mask decoder just takes this image representation and it takes this representation of what the original prompt is, and then it gives you the actual mask. But here this looks more complicated. You see here how there's different P5, P4, P3. I don't know exactly what those are, but the size here tells me that this is some kind of hierarchical, almost like a feature pyramid kind of situation, right? Where you have a smaller version of the image, slightly larger, slightly larger. The text encoder is clip. So generally here, you see how the text is going into this prompt encoder. It's probably not going in raw. It's going in already encoded. So you're going to take this text, the raw sentence, and then feed it into a tokenizer and then a text embedding model. And that text embedding model is clip. That's what they're telling you here, which is very popular. I like how many emojis these guys use. Download a model checkpoint. So let's see. These are the different models that they have. So this is the original huge. It's about 600 megabytes or half a gigabyte. These are the different patch sizes. So obviously the more patches you have, the longer the inference is going to take. Maybe we go through this. Let's see what this one looks like. Okay, so this is the faster segment anything. Here's a bunch of updates that they did. Grounding SAM in the browser. Jolly Gen. There's a... I feel like I recall hearing someone saying, or like, you can now use your GPU from your browser. I haven't like really looked into that, but maybe that's what this is. Mobile SAM in the browser. ONNX. ONNX is Open Neural Network format. It's a very common format if you want to take a PyTorch model and then use it in TensorFlow, or take a TensorFlow model and use it in PyTorch. This is like kind of like the in-between format. Open source standard for representing deep learning models. I think if you actually want to import a model into TinyGrad, you also use ONNX. But I think we actually had a stream where we used ONNX to convert a PyTorch model into a TensorFlow model so that we could quantize it and run it in the segment anything 3D. Sounds kind of cool. Single GPU with 100K data sets. Training code will be available soon. Yeah, so you see here this distillation here. So this is actually how they train the tiny vision transformer. So they have some loss, right, which is basically saying that whatever comes out of this huge image encoder, this image embedding should basically be as similar as possible to this image embedding. So they're not, this is frozen, and this is the one that's going to be basically getting the distillation gradients. So over time, this image embedding will become very, very similar to this image embedding, but the image encoder that you're using will be smaller and smaller, or it won't be smaller and smaller. It's not like it decreases in size, but it'll be smaller than this original one here. Okay, do they have a way to test this locally? And you can export it. This is the tiny VIT that they use. Where is this coming from? Cream. The fuck is cream? This looks like a Microsoft. MIT license. Neural architecture design and search. So neural architecture search, sometimes also called NAS, is a technique where initially all of the model architectures were basically designed by hand, but then people started realizing that a lot of the design decisions are a little bit not intuitive, so people started basically searching through the space of architectures, right? And they were able to find weird like kernel sizes and strides and stuff like that in the case of convnets for convnets that would perform better than hand-designed convnets, right? So it seems like basically what this is, tiny VIT, is basically someone did neural architecture search in the space of tiny transformers, tiny vision transformers, and they probably found a very cool, clean, little tiny vision transformer. And this is, I guess this is what it is, tiny VIT right here. Pre-trained teacher model. It's very hardcore augmentation here. This almost looks like cut mix. Boo, what's going on? Alright, wait up, I gotta show you guys Boo here. It's been a long time. What do you want to say to the stream? Do you want to say anything? No? Okay. Alright, that's Boo. Babies and kittens, yeah, man. It's crazy. I'm like not on a lot of sleep right now, so it looks like there's a bunch of different image relative position encodings. This is kind of cool. It's like almost like position embeddings, but like an object-centric position embedding. This is kind of cool. I've never even like heard of this Cream group. What is Microsoft Cream? Is that like a team? Like what does the cream mean? Is that like the team, or is that just like this random repo, or right? Like what the fuck? Okay. But kind of interesting that, which one was the one that used this? Was this the Chinese one or was this the Korean one? So faster segment anything or mobile SAM is the one that uses the TinyVIT, which is, okay, so it's the Korean people that are using the Microsoft neural architecture search TinyVIT. Coupled knowledge distillation of SAM. The left subfigure denotes fully coupled distillation, while the right one represents the semi-coupled distillation. Okay, so what is different between the left and the right here? Mask, 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 prompt guided, frozen, trainable, copy. Okay, so I think obviously here the large image encoder is going to be frozen. They don't really care about pushing gradients into that because they're not going to use it. Really where they're going to be pushing gradients is into this small image encoder, which is the TinyVIT from that Cream repo. I think here the distinction between the left and the right is whether this mask decoder is being trained as well. So here it looks like they're basically keeping the same exact mask decoder. In fact, they're just probably copying it. But here it looks like they're actually pushing gradients into the mask decoder, right? So they're pushing gradients all the way from here. And then it goes back into the image encoder. When performing a knowledge distillation from the original SAM to that with a smaller image encoder, the difficulty mainly lies in the coupled optimization of the image encoder and combined decoder. Yeah, so kind of similar to what we were saying with the prompt encoder and the mask decoder, the image encoder and the mask decoder are also kind of coupled, right? If you change this image encoder too much, the mask decoder is not really going to understand what the image encoder is giving it anymore, right? The mask decoder isn't really getting an actual image. It's getting a representation of that image, right? You could think of it like an alien language. And over the course of training, the mask decoder has gotten pretty good at understanding what this image embedding represents, right? But if this image encoder starts drifting away from the mask decoder, then the mask decoder is going to have a really hard time. So normally, it doesn't matter because when you're doing this knowledge distillation, right, you want the old image encoder and the new image encoder, which is the smaller one, to basically produce the same image embedding, right? But, right, that's more what they're doing in this first paper here, right? Let's see if we can scroll to a picture of that. Do they have a picture of that? No, they do not. Okay. Why does this look so much more complicated? All right, we're getting distracted. Let's go back here. Intuitively, the optimization of the image encoder depends on the quality of the image decoder and vice versa. When the two modules in SAM are both in a bad state, it is more challenging to train them both to a good state. Inspired by the divide and conquer algorithm, we propose to divide the KD task into two subtasks: image encoder distillation and mask decoder fine-tuning. First, perform KD on the image encoder by transferring the knowledge from VITH to a smaller encoder. Okay, so this is where they're taking the output of the big image encoder and saying that should be the same as the output of the small image encoder, right? So just making the image embeddings the same. That's this first step. Since the mask decoder in the original SAM is already lightweight, we plan to keep its architecture. Okay, so the mask decoder is kept the same. To alleviate the optimization issue of coupled distillation, a straightforward way is to optimize the image encoder with a copied and frozen mask decoder. The freezing operation can help prevent the quality of the mask decoder from being deteriorated by a poor image encoder. We call this distillation semi-coupled because the optimization of the image encoder is still not fully decoupled from the mask decoder. Empirically, we find that this optimization is still challenging because the choice of a prompt is random, which makes the mask decoder variable and thus increase the optimization difficulty. So I guess they mean the choice of a prompt is random, so which type of prompt it is that what they're saying? Is it whether it's a point or a box or a text or... It just changes from image to image. Therefore, we propose to distill the small image encoder directly from the VITH in the original SAM without resorting to the combined decoder, which is termed decoupled distillation. Yeah, I mean, this is kind of, I feel like this is more obvious than what they're doing here, right? Like, you wouldn't want to distill the mask, right? So you wouldn't want to say, hey, the output of your entire pipeline with the big image encoder should be the same as the output of the entire pipeline with the small image encoder. I would do what they're doing right here, right? Where, hey, the distillation doesn't happen at the mask level, the distillation happens at the image embedding level. Just make these image embeddings the same. Like, this to me feels like the more obvious way to do it rather than this up here, so. Yeah, so I think this is what the other paper is also doing as well. They're keeping the mask decoder and prompt encoders the same and freezing them because they're already small and they're not the slow part of the system. And then really all they're doing is just doing the training a small image encoder here with distillation. You know what is the stable diffusion XL? So I was actually looking at this because I wanted to try to do like a project with this, and you could probably, what is the latent diffusion model that uses 2 fixed pre-trained text encoders? What is the image encoder used in diffusion, or in, is it this one? Clip VITL and open clip VITG. Probably don't want to use a conv next, but these are same models, so you could probably do that. Unlike the semi-coupled distillation, the above decoupled distillation yields a lightweight image encoder that might not align well with the original frozen mask decoder. Empirically, we find that this is not true because the generated image encoding from the student image encoder can be sufficiently close to that of the original teacher encoder. Yeah, I mean, that's the whole point, right? It's like you're making this image embedding match this image embedding, which renders fine-tuning on the combined decoder optional. Train this on 128 GPUs. Yeah, so not only is coupled distillation just intuitively worse, but it's like worse for other reasons too, because it means that you have to perform inference, right? If you're doing this coupled distillation, you have to basically perform inference on this mask decoder and on the prompt encoder. But if you're doing this decoupled inference, you don't actually need this at all. You don't need to load the mask decoder into memory. You don't need to load the prompt encoder into memory. All you're doing is just loading these 2 models into memory, and then, in fact, you don't even need to do that. You can take your entire data set and encode it beforehand, and then all you do is you load this small image encoder into memory for training, and then you basically have a data set that consists of image embeddings and then images. So it's like this is the target, and then this is the input, and this is the target. So you can pre-encode your entire data set for this decoupled distillation to make it even faster at train time. I wonder if they do that. But only 2 GPUs, batch size of 4, 55K iterations, 11,000 images. Yeah, you want to be careful whenever you're doing this type of distillation. Like, you want to make sure that the images that you use for this are very broad and good representation of the original dataset distribution, right? Because sometimes if you just take random images, you'll pull a subset that just looks at a specific area of the image distribution, and then the image embedding that'll come here will work sometimes, but other times it won't work because it just this distillation process just got good at one little area of the image distribution. So you have to be careful with the subsampling of the dataset that they definitely did here, right? Where they only took 11,000 images out of the original 11 million. Yeah, 1% of the original dataset. Like, there is some risk there. It's like, how did you make sure that that 1% is representative of the full dataset? And then here you go. Here's exactly the trick I was referring to, where you save the image embeddings beforehand, so you only need to run the forward process once. Yeah. So if you didn't do that, you would basically have to load both of these models into memory, and then for every image, perform inference with the big one to get the image embedding, and then perform inference with the small one to get the image embedding. But that would be an absolute pain, right? Because not only is this big image encoder going to be huge and take up a bunch of memory, but now the inference is also going to take time. So pre-encoding your data set is very useful. It changes the compute and memory. So like, rather than having to do it all at the same time, you basically, it's like a pre-processing step. So heavily agree with that. Training, longer time, better performance. Performs on par with regular original SAM. Okay, so obviously some cherry-picked examples that they provide are going to be cherry-picked and they're going to be impressive, you know, but that's not necessarily telling us how good it actually is. Ablation study on the influence of training computation on the mobile SAM. So here you have bigger batch size, same amount of iterations. MIOU, this is intersection over union. It's kind of when you have bounding boxes or even masked or anything that's like basically one area and another area, it's just kind of like how much overlap is there, right? And then the M refers to the mean of that. So for X amount of examples, what is the average amount of overlap between the actual ground truth or ground truth in terms of like what the original SAM does, and then the output of the mobile SAM. So you can see here a little bit higher overlap if you train it for a little bit longer and on a bigger batch size. So batch sizes are important, more important than people realize. Like, some people, like, you can think of one way to think of batch size is that, oh, well, you're just getting more data faster, right? Because you're kind of feeding more data faster because it's the batch is bigger, right? But it's actually better than that, right? Because the way that your optimizer works, right, it's like you're taking these little steps in this high dimensional kind of like hilly landscape with your little marble, but the bigger batch sizes result in better steps, right? So if your batch size is very small, sometimes the gradient step that you get out of that will kind of take you in a direction that isn't necessarily the direction you want to go in this lost landscape. But the bigger your batch is, the more examples, the more representative that batch is of the full training data set, which means that the actual little step, the little gradient step that you take as a result of that batch is actually more likely to be in the right direction that you want to go. Right, so batch size is not just about like throughput. It's not just about, hey, you can get more images through. It actually results in a faster path, if you want to think of it that way, if you're thinking of the analogy of the little marble rolling through the hill. But of course, the reason people don't use absolutely massive batch sizes is because you need absolutely massive GPUs. So a lot of times the batch size is just limited by what you can fit on the GPU that you have, or the multiple GPUs that you have. Increasing the number of GPUs for allowing a larger batch size or further increasing the iterations can further improve the performance. Segment anything versus segment everything. Oh. Is there a difference? So they're saying there's two different papers here? Segment everything versus segment anything? What? Segment anything, everything does not necessarily require a prompt. FastSAM directly generates the mask proposal with YOLO V8 in a prompt-free manner. Oh. Okay, so this is a little bit interesting. Where is that? Right here. So they don't even use the prompt encoder. FastSAM consists of a YOLO V8 based detection branch and a YOLO Act based segmentation branch to perform a prompt-free mask proposal generation. It has 68 million parameters. It takes 40 milliseconds to process an image. So this is two slightly different ways. Actually, that's kind of interesting. So this paper isn't just one way. They actually have two slightly different things here. I think the FastSAM is the one that we've been looking at, where they keep all the original parts and then they just replace this image encoder with the tiny VIT. But then it sounds like they also have a more complicated pipeline called MobileSAM that uses a bunch of the YOLO V8 machinery, which makes sense because these YOLO models are very, very popular in production. Right, so pretty much any computer vision company that's doing any kind of real world detection in some agricultural use case or in some factory or maybe in an airport and you're detecting people, they've had years to improve the inference speed of these YOLO models. So even though it's kind of an older model architecture and kind of system design, right? It's very fast, and because it's been used in production for years at this point, right? They've optimized it, quantized the things that need to be quantized, picked the right little kernels in order to make it as fast as possible. So it makes sense that if you really want this to run on a mobile phone, you could just lean on that a little bit more. Yeah. So what is this here? MIOU, with the assumption that the predicted mask from the original SAM is ground truth, a higher MIOU indicates a better performance. So this is again the basically the overlap, the average overlap between the mask that comes out of the big segment anything model and then the mask that comes out of their two different approaches here, FastSAM and MobileSAM. So you can actually, I don't know what this 100 is. Let's see. What is this here? Mask, blah, blah, blah. Predict the mask, multiple points. What the fuck is this here at the top? Is this the size of the model? What is the 100, 200, 300? What is this number? Distance between two prompt points. Okay, so this might be the number of points. Okay, so if you remember, I was talking about here when we were looking at this demo, for the mobile SAM, right? How you basically, you put these points, and in the original segment anything paper, the way that they do, they prompt an image where you don't have a human in the loop is basically they put this grid of points over the whole thing. So it sounds like here what they're saying is that, okay, if you have 100 points, so 100 random, they're not random, they're like in a grid, but 100 of points in a grid, the fast SAM, which is basically the version that only switches out that image encoder, it actually doesn't do that well, right? So there's a relationship between the number of points that you're using to prompt and the actual quality of the mask, right? If you assume that this overlap indicates better performance, versus the mobile SAM, which is their weird hybrid model that basically is like some variant of the YOLO stack, it pretty much works every time. I think here the 100 probably refers to the number of proposals. So back to mask RCNN, right? You have this part here, the region proposal network. Sometimes you see that as RPN. So in the original mask RCNN implementation, right, this region proposal network is the one that gives you basically these bounding boxes, and then those bounding boxes here, you see how they get basically squashed into a perfect square, and then you have a separate network that basically tells you the mask. So this first part of the pipeline here, this RPN, all it does is it basically just gives you bounding boxes that may contain an object that is worth segmenting. So the number of regions that are proposed is probably what they're referring to here. So this is 100 regions or for mobile SAM, and then 100 points for fast SAM. So I mean, it's like difficult to really compare that because there's all kinds of priors that are already there. So in this region proposal network, these boxes are coming from a human set of like anchor boxes, sometimes they're called. Let me see if I can find this. Anchor boxes. Yeah, so these anchor boxes come with a human prior in them that you're assuming that there's going to be things that are square-like, there's going to be things that are kind of fat, wide rectangles, and there's going to be things that are tall rectangles, right? But these ratios of the rectangles are just kind of arbitrarily chosen, right? So some human came down and said, okay, well, I think that there's probably going to be things that are roughly of these types of scales, right? So like humans that are walking generally are like this, and then a car generally is like this. So there's already a little bit of a prior coming into the region proposal network, right? I think that's a stronger prior than what fast SAM is getting, which is just a grid of points. Results for segment anything. So you have the original image, you have the original segment anything, which is this middle one. So this is basically the ground truth. And then you have mobile SAM, which is the YOLO variant. Naughty G8YTH. Welcome to the stream. So we're reviewing two different papers that got released recently that are basically faster versions of the segment anything model. The segment anything model is a foundation model released by Meta or Facebook AI Research that basically does segmentation, which is the task of basically creating these masks, right? Where you can basically say this part of the image corresponds to this object or something like that, right? So it's basically like the bounding box, but better. So both of these papers, right, one of which comes out of a Chinese research group and then the other one which comes out of a Korean research group, both of them have basically the same approach where they're basically taking this image encoder, this big green block, which is this giant vision transformer, and they're replacing it with a smaller image encoder. So the entire segment anything pipeline, right, is this, you do this image encoder, you get this image embedding, then you encode a prompt, which can be anything from a points or a box or a text, and then mask decoder consumes all of that and gives you these masks. But this prompt encoder and this mask decoder are very small, so they're not necessarily what's slowing you down, right? So if you were trying to make a faster version of the segment anything model, really what you're interested in is making this image encoder as small as possible. So in one of the papers, they replace it with the backbone of a YOLO V8 model, which is a very popular detection, segmentation, pose model that's used in production. And this is V8 refers to the 8th version, so there's YOLO V1, V2, V3, so on. So it's been improved over time. It's quite fast. And then in the other paper, they replace it with a smaller image encoder that is also a vision transformer. It's called a tiny VIT that comes from this weird repo that Microsoft has called Cream. Yeah. So they're replacing it with this one, tiny VIT. Okay. So back to this. So now what we're comparing is in one of the papers, they basically are comparing their fast SAM, which is the tiny VIT, with mobile SAM, which is the YOLO V8. I think so. I'm getting my papers confused, but largely what we're seeing here is quality kind of seems the same. I don't know. It's hard to really tell. I'm looking here at the windows. Right, like maybe here you see here in the clouds, mobile SAM and the original SAM can segment out the individual cloud, but here it just kind of gets lumped into the same. Conclusion: in this work, we aim to make SAM mobile friendly by replacing the heavyweight image encoder with a lightweight one. We find that the naive way to train such a new SAM, as in the original SAM, leads to unsatisfactory performance, especially under a setup of limited training resources. Yeah, you wouldn't want to just train this from scratch. That'd be very poor. The coupled optimization of the image encoder and mask decoder is the reason, and thus we propose decoupled distillation. Another typo here, where the knowledge is distilled. From the image encoder VITH into a lightweight image encoder. We show that our resulting lightweight image encoder can be automatically compatible with the mask decoder in the original SAM. Yeah, and the reason that it's automatically compatible is because you're just taking, you're basically just doing a distillation type approach and saying, okay, well, whatever the embedding that comes out of this big image encoder, let's make sure that the embedding that comes out of the small image encoder is exactly the same. Wow, you look like Hyphonics. What is Hyphonics? Is this like a person? Yeah, I mean, we're both white and we're both bald. I don't know. I think his stash is better than mine, to be honest. He's got a better looking stash. But he looks a little doughy. You know, looks like this man. Looks like he maybe eats a little bit too much food. Okay, our mobile SAM is more than 60 times smaller, yet performs on par with the original SAM. We conduct a comparison with a concurrent fast SAM and show that mobile SAM achieves superior performance. Our mobile SAM is also 4 times faster, 7 times smaller than the concurrent fast SAM, making it more suitable for mobile applications. Since mobile SAM keeps all the pipeline of the original SAM and just replaces the image encoder, it can be plug and play for the existing SAM-based projects to move from a heavyweight SAM to a lightweight one with almost zero effort. Yeah, and I mean, it's like, it's a good idea too, right? I think this is a very common strategy for anybody that's done computer vision pipelines that have to run on edge devices. A lot of times you kind of come to this situation where you have multiple vision models and all of them are just using different backbones. And a very simple thing you can do, and this is something that you run into in robotics all the time, is that you take every single one of those vision pipelines and then turn them into a combined vision pipeline where all of the different models are become heads to the same model. And this is actually Tesla AI. This is what Tesla does as well. So in the original Tesla AI presentation, 2022, this one. See if I can find it. This is the older one. But basically, you use the same vision encoder for all of these pipelines, right? So the vector space encoding, AI compiler, and inference. No, this is, I want the 2021 presentation. See if I can find images here. Yeah, here you go. Boom. So you see here how you have different cameras coming in, and all of them are using the same image encoder here, this RegNet. So you could take each of these cameras and then feed them through an image encoder that's different for each one, but then you'd have your inference cost is going to be 3 times as much, right? So by using the same image encoder for each of these different vertical stacks here, you basically save a bunch of time in inference. So I don't know, I kind of took a long way to explain a simple concept there, but this idea of replacing image encoders, consolidating them with knowledge distillation is very common strat. Is there anything here in the, is there any appendices? No. Okay, now let's go to this paper. Let's see. Let's go through this paper a little bit more closely. Okay. Real-time CNN-based solution. First study of applying a CNN detector to the segment anything task. Yeah, NMS is fucking no good. This is non-maximum suppression. It's garbage. This is what NMS looks like. NMS computer vision. So in these old school detection pipelines, you generally end up predicting a bunch of bounding boxes like this, and then you have to reduce the total amount of bounding boxes to a single one. So you use this technique called non-maximum suppression, which looks at the confidence of each bounding box and then also how much overlap they have between them, and then we'll reduce it to a single bounding box that is better than any of these individual bounding boxes. But the problem is that this NMS is, you have to run it after each detection. So basically it's like an additional compute that really you want to get rid of. But you see here how NMS is used to pick out some subset of all the bounding boxes and masks that you get here. All instance segmentation versus prompt guided selection. So prompt guided selection is where you're feeding in a prompt here, either points or box or text. We use various prompts to identify the specific objects of interest. Mainly involves the utilization of point prompts, box prompts, and text prompts. The text prompt is based on clip. Can you see this being used as a utility function in a larger model? What do you mean by utility function? So the way that I could see this being used is, this is kind of a crazy idea, but it's something that I've been thinking of, is something like a control net, right? Like you have these EB synth, right? This is like, you're seeing more and more of these come out, but it's this, you're trying to basically style transfer into videos and use diffusion models for videos, right? And you have to do this frame by frame. And generally people end up using what's called a control net, which is a type of diffusion model that you can control with something like an edge map or a pose map or a depth map, right? So control net. Yeah, like this, right? So it allows you to basically guide diffusion models with a segmentation map, right? So the problem with things like EBSynth is that they don't run in real time because you basically have to do it frame by frame, and then you have to take each image, run it through a model that gives you a segmentation map, and then take that image and then run it through the diffusion model with this control net attached to it. But I wonder if you could use the same image encoder for all of these things, right? Use the same image encoder for the diffusion model and for this segmentation model, and then basically combine all of those into one thing. And then could you get close enough to where you could get a real-time control net for video? Right, like you see here, for example, here in this pipeline, they say, okay, control net v1, okay, you have to use open pose key point detection. So inside this open pose key point detection, there's a vision encoder, there's a backbone, right? There's some convnet that's taking this image and converting it into this pose. Inside this stable diffusion model, there's also an image encoder. So what if you replaced this part here with segment anything, and then you use the same image encoder for this part here that you used for this part here? Right? I think there's pieces missing there, but I feel like that could be a way to get to a real-time video to video. I don't exactly know what the problem, but it's that the task of basically controlling diffusion models. I don't know. So that's a random idea that I had about how you could use this faster segment anything, but there's a million other ways that you could use this. FastSAM training was carried out on 2% of the SA1B. SAM uses the transformer architecture to construct an end-to-end algorithm. To segment anything, SAM learns the vision-oriented inductive bias through the learning process on large-scale data. FastSAM surpasses SAM at all prompt numbers. The speed of FastSAM does not change with the prompts, making it a better choice for the everything mode. Oh, okay, wait up. I think originally I might have said that this 16 by 16 was the patch size of the vision transformer, but that's not what it is. This is actually just the number of points in the grid for whenever you do the everything mode. So I take that back. This 64 by 64 means the grid of points that you're laying out as prompts for everything mode. So that's just the number of points that you're using. Edge detection. Right, so you go zero shot transfer to edge detection. So the segment anything model is quite good at edge detection, which is exactly what you need for a control net pipeline. Right here are edges. And the standard model that people use for edge detection in control nets is this model here, HED. Zero shot edge prediction. Fast SAM achieves comparable results to SAM. Yeah, I would say both of these are fine. Really, the only difference here is basically just like kind of a threshold thing. Real-world applications. We valued the performance of fast SAM across different applications. Anomaly detection. Between defective and normal samples in manufacturing. A little bit of a typo there. Fast SAM can segment nearly all regions. Salient object segmentation. Segment the most attention-grabbing objects from an image. You could probably just put a bunch of points in the center of the image and then just rely on the object-centric bias. So here you're prompting with a point. That's what that little yellow dot is. Here you're prompting with the bounding box. That's what that green box is. And here you're prompting with a grid of points, which is 16 by 16, 32 by 32, or 64 by 64. They don't, I wish they would have done fast SAM text, right? I would have been curious what you could get if you prompted this with text that said like 500 or like pill or something like that. Little geospatial application here. GIS. I'm not as familiar with this kind of application, but I think generally what people get paid to do is like count cars in parking lots and total surface area of building versus not. I feel like this type of like satellite imagery stuff is like that's what, like, to me that kind of like screams like military applications, like, but discussion. Conclusion. We rethink the segment of anything task and the model architecture choosing and propose an alternative solution with 50 times faster running speed. The experiments show that fast SAM can solve multiple downstream tasks well. Still, there are several weaknesses that can be improved for fast SAM, like a scoring mechanism and the instance mask generating paradigm. I don't know, I feel like this is just more crap like the NMS that's just going to slow you down in the long term. I feel like you want to get rid of this complexity. Okay, no appendices either. Okay, so we don't have a ton of time left. I do have to head out, but let's see if we can maybe do a little summary here and point people in the right direction. So today we looked at two different papers for two different repos that are fast implementations of the segment anything model out of Facebook. The segment anything model takes an image and produces a bunch of segmentation masks with scores. It has three main components: an image encoder, a mask decoder, and a prompt encoder. The biggest and the slowest component, biggest in terms of most memory consumption and the slowest in terms of the compute spent, is this image encoder. And both of these two repos, one of which comes from a bunch of Chinese researchers and one of which comes from a bunch of Korean researchers, both of them basically do the same thing, which is replacing that image encoder with a smaller model. Both of the GitHub repos are pretty good. They both have the seemingly nice code here, right? Just conda environment, and then you just have your simple little Python script that'll do it for you. And both of them have these Hugging Face demos. And we tried out both of the Hugging Face demos, and they're both pretty fast, right? You can see here, even just with that, it took about 4 seconds for this image here, which is pretty fast. And then this is the other one. And this is faster just because we put the dots there, but here we could put dots on this dog, put a dot on this tree, put a dot on this tree, and then we should get more interesting results here. But they're both pretty fast. Wow, that's actually kind of terrible results. Let's see if this one's better. Let's put one on the wheel, one on the window. Let's see. Yeah, that's much better. But both of these are kind of cool. Very difficult to kind of say one is better than the other. I would say both of these are almost identical, but you know, good stuff. Making that image encoder small is probably the best way to make your whole pipeline faster. So if you're doing anything, it might not even be segmentation, but if you're doing any kind of computer vision pipeline, right, I think you should kind of consider what these guys did and take that image encoder that you're using and see if you can use distillation to make it as small as you can, and that will give you the most performance juice, right, in terms of speed. But it is going to come at a cost of performance, but this cost really isn't that much, right? You're talking about the original SAM here at 67% recall versus the new SAM here, fast SAM, at something like 63% recall. So you're losing 5% recall performance, which doesn't really seem like much of a price to pay for basically multiple 10x. This is 7,000 milliseconds per image to something like 12 milliseconds per image, which is pretty crazy. That's close enough to almost run in real time, right? Here they have the real time, this bar, so anything to the right of this bar is real time. What is, let's go here. What is 30 frames per second in terms of total milliseconds spent on each frame? Total milliseconds spent on each frame at 30 frames per millisecond is 33 milliseconds. So 33 milliseconds is, you would have to be under that in order to get 30 FPS. And I think both of these achieve that. Yeah, this one gets 12 milliseconds, which is 1/3 of that. So you can even run this at 120 or 60 FPS, which is more than enough. 60 FPS is like, most people can't even tell anymore. And then here you have 12 milliseconds per image, which is also, you could run that at 60 FPS. It's pretty cool. That's all I got, guys. I'm tired. I need to go eat and sleep, but it was nice to hang out, you know, see you guys. I'll be doing another stream tomorrow as well. I think we have a paper on 3D object generation from a 2D image. Should be kind of cool. And then also, I think there was a computer vision conference relatively last week or something like that. So there should be more papers that are coming over the next couple weeks that we will be reading. Feel free to join the Discord. There's a link in the description. Join the Discord. Come recommend papers. Come hang out with us. And if not, have a great day. See you guys later. Thanks for hanging out. Thanks, Zorg, Mantan, Kami Mekin, Fox, Nadi, Apoya, Ryan for the questions. And see you guys later. Peace.